Good morning, students. In the last class, I have just told you about the colligative properties. Colligative properties are the properties which depend upon properties of dilute solutions which depend upon number of particles, not on their nature. And in these colligative properties, there are 4 colligative properties, and these colligative properties are used to determine molar mass of the substances and degree of dissociation in case of electrolytes. Now, so in the 4 colligative properties, first one, relative lowering of vapor pressure of solvent. Relative lowering of vapor pressure of solvent. In the last but before class, I have just discussed about solutions of solids and liquids, that is non-volatile solute. If dissolved in a volatile solvent, what happens to the vapor pressure? I have just discussed. So I will recall you. Vapor pressure of the solution. Vapor pressure of the solution prepared by dissolving. Vapor pressure of the solution prepared by dissolving non-volatile solute in a volatile solvent. Non-volatile solute in a volatile solvent is always less than that of pure solvent. Less than that of pure solvent. Remember this point clearly. So, vapor pressure of the solution is always less than that of the pure solution solvent. That here, if P1 is the vapor pressure of solution and Pi is the vapor pressure of Pi naught is the vapor pressure of pure solvent, then we can say that Pi less than Pi naught. And for the same vapor pressure of solids and liquids, I have given you the rods. So the format of rods will be P1 is equal to P1 naught into x1. This is equation 1. This equation establishes a relation between vapor pressure. P1 is the vapor pressure of the solution. P1 naught is the vapor pressure of pure solvent. And x1 is the mole fraction of corresponding solvent. Mole fraction of solvent. So here this is the Rod's law related relation, and this establishes a relation between vapor pressure of the solution, then vapor pressure of the pure solvent, and mole fraction of the solvent. Now, as per this relation, lowering off or reduction of vapor pressure of solvent, that is delta P1 is equal to P1 naught minus P1. So here, as the quantity P1 naught is larger than P1, here we can write delta P1 is equal to P1 naught minus P1. So that is equal to P1 naught minus P1 naught into x1. This is from 1. And here P1 naught into 1 minus x1. That is equal to P1 naught into x2. Equation 2. That is delta P1 is equal to P1 naught minus P1 is equal to P1 naught into x2. So here 1 minus, so relation between mole fractions will be 1 x1 plus x2 is equal to 1. So by that relation I have taken here 1 minus x1 is equal to x2. Or we can also write delta P1 divided by P1 naught is equal to P1 naught minus P1 divided by P1 naught is equal to x2. So this is equation 2. Now in the equation 2, there are LHS and RHS. So if there are more than 2 solids in the reaction, if more solutes are present, solution. So, and is equal to mole fraction of the solute. That is given by the Raoult's law in the last but before last class. Now, so LHS of equation 2 is known as relative lowering of vapor pressure, and relative lowering of vapor pressure is nothing but it is the difference between vapor pressure of pure solvent and that of the solution. Now, so as N1 and N2 are the number of moles of solvent and solvent 1 and solute 2. N1 and N2 are the number of moles of solvent and solute 1 and 2. W1, W2 with the masses of solvent and solute. M1, M2 with the molar masses of solute and solvent respectively. Then we know two relations. X2 is equal to N2 divided by N1 plus N2. So, and N is equal to W divided by M. So, equation 2 implies delta P1 divided by P1 naught is equal to P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1 plus N2. So, because mole fraction is given by this relation, number of moles of the solute divided by total number of moles of the solution. Now, for dilute solutions, what is the condition? So, we are applying the colligative properties only when the solutions are dilute. So, in dilute solutions, condition will be number of moles of the solute is very less than number of moles of the solute. Is it? Number of moles of the solute is very less than number of moles of the solvent. So, neglecting N2 from denominator. Neglecting N2 from denominator. So, equation 2 becomes delta P1 divided by P1 naught is equal to N2 divided by N1. So, now I have also given the relation between N2 N, that is number of moles of the solute is given by mass of the solute divided by molar mass of the solute. So, that it is W2 by M2 into M1 by W1. So, if all the quantities are known, we can calculate molar mass of the solute as M2 is equal to W2 by W1 into M1 into P1 naught divided by P1 naught minus P1. So, this formula is very useful in calculating molar mass of the substances if vapor pressure of the pure solvent and vapor pressure of the solution, masses of the solute, masses of the solvent and molar mass of the solvents are given. This is the first colligative property. Now, second one, elevation in boiling point of the solution. Elevation means increase in boiling point of the solution. Second colligative property, elevation in boiling point of solution. So, I will draw here graph of vapor pressure versus mole fraction. So, here graph of solvent is like this, solution is like this. If you plot the tangent, then this is TB naught, this is solvent graph, this is solution, and here it is 1.013 bar, and it is TB naught, TB, difference will be delta T. So, graph. Vapor pressure and temperature graph. So here in this graph, so vapor pressure of the solution is lower than or below the curve, below the curve of vapor pressure of solution is below the curve of vapor pressure of your solvent. So this can be seen in the graph which is given in the diagram. So here solvent lies in the above and solution lies below. So let me give an example how the vapor pressure of the solution is going to vary along with the temperature. And in discussing vapor pressure of the liquid, we have also discussed about vapor pressure, how it varies with temperature and presence of non-volatile impurities. So vapor pressure of liquid is varying, increasing with the temperature and decreasing with the non-volatile impurities. Okay, this point I have already given you. So vapor pressure of the liquid will increase with the temperature and it will decrease at the same time, it will decrease with the presence of non-volatile impurities. Now, so what happens when a non-volatile solute is added to the volatile solvent, and what is about the boiling point? Boiling point of the solution also liquid. So boiling point and vapor pressure are inversely proportional. Now here in the relation, so let me give an example. Boiling point of water is equal to 373.15 Kelvin. We already know. Now at this boiling point, what will be the vapor pressure of water? Vapor pressure of water will be 1.013 bar or it is 1 atmosphere. So as the vapor pressure has reached the atmospheric pressure, we are saying water is boiled. Now if sucrose is added to the water, so that vapor pressure of the solution is going to decrease because sucrose is a non-volatile solvent. Okay, if you add sucrose to the water, boiling water, vapor pressure of the water is going to decrease. How it will decrease? It is less than 1.013 bar. Now our aim is to bring this vapor pressure 1.013 bar to 1.013 bar. For that, what should we do? So we are just boiling the solution above the boiling point of water, so that sucrose solution will boil at a temperature of 373.52 Kelvin. So here always remember one point: boiling point of the solution. Again, conditions apply. Boiling point of the solution prepared by volatile solvent and non-volatile solute is always higher than that of pure solvent. So the same is given or indicated in the graph. This point is also to be remembered. Boiling point of the solution, volatile solvent, non-volatile solute is always higher than that of the pure solvent. If let TB not be the boiling point of pure solvent, let TB not be the boiling point of pure solvent, TB be the boiling point of solution. So that what will be the condition here? TB greater than TB not. Okay. So boiling point of the solution is always higher than that of the boiling point of the pure solvent. by delta TB is equal to TB minus TB naught is the difference between boiling point of solution and that of pure solvent. If that elevation, or it is also called by the name increase or elevation in boiling point of the solution is delta TB is equal to TB minus TB naught. It is the difference between boiling point of the solution and that of pure solvent. Okay, so this let be taken as equation 1. So here from experiments, elevation in boiling point is proportional to molarity of the solution. Elevation in boiling point is proportional to molarity of the solution, that is delta TB proportional to M, where molarity is given by W2 divided by M2 into W1 divided by 1000. Okay, so if you remove the proportionality sign, this becomes delta TB is equal to KB into M, that is equal to KB into W2 into 1000 divided by M2 into W1. And this is the relation between elevation in boiling point and molar mass of the solvent. So now in this equation the proportionality constant, KB is defined. When KB is defined, so when M is equal to 1, that is molarity of the solution is 1. In that case, delta TB or KB is equal to delta TB, or it is the KB is the value when 1 mole of the solute is dissolved in 1 kg of the solvent. 1 mole of the solvent is dissolved in 1 kg of the solvent. Elevation is equal to elevation in boiling point. So remember the point. Here KB is called as boiling point elevation constant. Boiling point elevation constant or molar elevation constant or ebullioscopic constant. So in Greek, ebullio means to boil. So that KB, units of KB. So KB is given by KB is equal to delta TB divided by M. Delta TB is defined in Kelvin and this is in moles per kg. So is equal to Kelvin kg per mole is the unit of KB. So here boiling point elevation in boiling point of the solution is ended. Now in the next class I will just discuss about depression in freezing point. Thank you.